Good evening. My name is Rich Alveders from the JPL Education Office. I want to welcome you to the lecture series tonight. Before I introduce our speakers, I want to remind you that the restrooms are toward the back and to the left. The emergency exits are to the back and to the side. In the unlikely event of anything happening. And we would be grateful if you could silence your cell phones and your digital devices before we begin. If this is your first time to JPL for this talk, we have these almost on a monthly basis, and information about these talks can be found at www.jpl.nasa.gov, as well as some other events that will be happening. So share the information with your friends. And thank you for coming. The moon is the most accessible and best studied or terrestrial body beyond Earth. Unlike Earth, however, the moon's surface has preserved the record of nearly the entire 4.5 billion years of solar system history. Orbital observations and samples of surface rocks returned to Earth show that no other body preserves the record of geological history as clearly as the moon. And yet, there is still a great deal we do not yet understand. Questions about the origin of the Maria and the asymmetry in crustal thicknesses require more advanced studies to understand. By carefully studying the gravity of the moon, its interior structure and thermal evolution can be learned. This information can then be extended beyond the moon to help us further understand the history and evolution of the other terrestrial planets in our solar system. NASA's Gravity Recovery and Interior Laboratory, or GRAIL, will use a technique pioneered by a highly successful Earth mission called GRACE, and will place two spacecraft in a low-altitude, nearly circular orbit around the moon to help reveal the answers to these intriguing questions. Tonight's guest is the Deputy Project Science for the GRAIL Lunar Mission. He is a co-investigator for radio science and experiments on many NASA and European Space Agency deep space missions, and also manages the Radio Science Systems Group at JPL, and has been awarded 2 NASA Exceptional Achievement Medals. Ladies and gentlemen, please help me welcome tonight's guest, Sami Asmar.
Thank you, and thank you all for coming to hear about GRAIL and the moon. From the size of the turnout, this just tells me it's probably nothing good on TV tonight. So we'll see how we can entertain you. So I'm Sami Asmar, and I'll be joined approximately halfway through the talk by my colleague, Mike Watkins. And as you can see from the logo, the name of the mission is abbreviation for the Gravity Recovery and Interior Laboratory. So we're going to be talking about a few concepts, especially gravity and the interior structure of the moon, and we'll be doing comparisons and analogies with other planets as well. So this is a picture most of you have seen of Earth from the surface of the moon from the Apollo era. And although there were many scientific discoveries and a lot of technological breakthroughs, there was probably an image like this that touched people the most, because that's when you start seeing Earth from a distance as a fragile blue dot in the sky. And then probably there was more support for the space program as a result of this. It's a beautiful picture. And after Apollo, in fact, there was an armada of spacecraft that have since been to the moon in one form or another. And this is an old picture. Actually, it stops in 1990. Even since then, there have been many more, from the European SMART mission to the Chinese Chang'e and the Japanese Kaguya, etc. So it is an Indian mission. It is a good and convenient target for actually nations just starting out in the space program as well. But those are all unmanned missions. The US had the only manned mission to the moon. The Earthrise picture I showed you earlier has been updated. Much higher resolution now topography, as you can see. This is taken from a Japanese orbiter, and that's the name of the Japanese Space Agency. So we're going to talk about the Earth-Moon as a system and the relationship, some of the similarities, and zoom in on the moon a little bit. The radius of the moon is approximately 1737 kilometers. This is the mean radius. it's a little bit less than 1/4 of the radius of the Earth. The highest point on the moon itself is 11 kilometers above the mean level. If the moon had a sea, we would call it sea level, but it doesn't. So the mean radius, and in fact, that's higher than the highest point on Earth. Mount Everest is approximately 9 kilometers. So we have a peak that's higher than the highest peak on Earth, and a valley or a point that's 9 kilometers below the mean. And that, again, is probably lower than any point on the surface of the Earth, barring ocean bottoms. So its surface area is about 37 million square kilometers. That's a little less than the continent of Asia. So Africa is probably comparable to the moon. And its mass is about 81 times less than the mass of Earth. Now this becomes interesting in the geophysical sense. The mean density of the moon is about 3.35 gram per cubic centimeter. I'm sorry, 3.33 gram per cubic centimeter, or it's about 3.35 times the density of water. So if you put it in water, it will sink, obviously. Interestingly, Saturn, a huge planet with the rings, that would float in water, but you'd have to find a bathtub big enough for that. Now, the age of the moon is about 4.5 billion years. It turns out that the age of Earth is about also 4.5 billion years. So right away, we know that the moon probably formed when Earth was relatively young, and we'll get to that. So there are various theories as to the origin of the moon. There are probably half a dozen. And some of them were competing for a long time, and the science community has settled on a favorite theory with this, which is this giant impact. Early on in the formation of the solar system, there were many bodies like Earth in its neighborhood growing and accreting. And one of them, people call it Mars-sized object, for some reason, collided with the Earth. Now this happened when the Earth was young and fluid, yet it had already differentiated. And by that I mean it had already separated its internal components into a core made of mostly iron and a rocky mantle. And this impactor object hit the mantle and not the core, and the debris that resulted and dispersed into space eventually coalesced itself and formed the moon. Knowing the density of the moon and the density of Earth, we think there's no iron in the moon, and that's why we think that it only hit the mantle part and did not take any piece of iron with it. So this is the leading theory, accepted theory currently. When the moon formed, it quickly filled with lava. It had a lava ocean, in fact, a magma ocean for millions of years, and volcanic activities for an extended period of time before it too started cooling and solidifying. Of course, now a big difference between Earth and the moon is that Earth is a living planet, and the moon is geologically dead as far as we're concerned. So there are no more volcanoes or activities. There's no volatiles, no atmospheres, no oceans, all the good stuff that we have on Earth, which is still living and moving. We are all witnesses to earthquakes in Southern California. What if the moon, though, this is a mind game, did not exist? Things would be different, it turns out. The day would be only 8 hours long. And if the work shift was 8 hours still, we'd be in trouble. It turns out that the presence of the moon actually has slowed down the Earth spin rate and the Earth rotation and the Earth length of day, and had slowed down the wind patterns and the climate. And as a result of that and consequent side effects, probably life as we know it altogether would have been different if the moon did not exist. Of course, the language would be different. We wouldn't be using the word honeymoons or lunatics. And the nights would be darker. The lunar calendar wouldn't exist. I don't know if there'd be a space race. And of course, I would not be given this lecture. But it turns out the moon is actually moving away from Earth, had been close at the beginning and has been moving away at a very slow rate of about less than 4 centimeters per year. In fact, as it moves out, the day will get longer. So in about 100 years, we're going to add 2 milliseconds to your workday. So the union breaks will have to be extended as well. In this time history where the moon was close and is moving away, it's really a great coincidence that we're in this era, this time period, the size of the moon angularly as you look out in space and its distance from Earth and the sun creates a perfect solar eclipse. In other words, the diameter of the sun at its distance and the diameter of the moon at its distance cause this complete blockage. This will change as the moon moves away, but this is one of the funny, great coincidences of the time we live in. Now, from a scientific point of view, we want to learn about the origin of the moon and then start putting pieces of the puzzle together with the origin and the formation of the solar system altogether, especially the rocky planets like Mercury, Venus, Mars, Earth, and the moon. In the inner part of the solar system, they probably have common histories. And so studying the interior structure is the key to this big puzzle. So we're going to use a technique called gravity, which obviously everybody is familiar with. But the measurement of the gravitational field, now we went from gravity to gravitational field, which is, gravity is one number. Most people use 9.8 meter per second square. But a gravity field is an extension of how gravity changes from place to place as a function of latitude and longitude on the planet. How that, the variations of that are a result of variations in the densities of the material on the surface of the moon and below the surface especially. So the most common thing to do is to get a gravity field, and we're going to get in great detail of how one does that, but also get a topography, the highs and the lows, the mountains and the valleys of the moon or any planet, terrestrial planet. And then we remove the effects of the surface topography, remove the effects of mountains and valleys from the gravity and see what's left. So what do I mean by that? You all know that gravity works because everything with a mass attracts adjacent things with a mass. Things gravitate towards each other. So the way we study gravity, we'll show, is using spacecraft and the gravitational effect from features on the spacecraft itself. So if you imagine this is just zoom in on a piece of the moon. The moon is quite a big circle, and this is a piece of it with a mountain and a valley and so on. And the solid line is the normal orbit of a spacecraft in circular orbit around the moon. As the spacecraft actually comes close to the mountain, it will literally sense its gravity pulling on it, and it will move away from its orbit by an amount proportional to how much additional gravity is acting on it. This is exaggerated for illustration. The changes we're talking about are very small. And as it flies over a valley, the opposite effect will happen, and then it will move away and then readjust back. And it will keep doing this as it flies over craters, mountains, and valleys. So this part, I think, is relatively obvious. Additional mass causes attraction. Absence of mass causes gravitational repulsion. Now, where it gets interesting is that if you fly over, say, a mountain, and you expect it to dip like I showed in the previous slide, but it doesn't. Well, what gives? Something is going on in the geophysics, in the subsurface of the planet itself that's causing this. And that's called isostatic equilibrium. The planet itself has compensated for the weight of the mountain sitting on it by introducing material below the surface of lesser density than the mountain itself, such that the net effect at the lower layer called the MOHO is the same. Planets like this concept of hydrostatic equilibrium. They like equal weights on them in all directions. But they don't do that all the time. There's times where they can and times where they cannot. So when the moon was formed, it was warm and fluid like Earth, and it started cooling, and it's still cooling, as Earth is too. So if the mountain was formed when the body was still warm, this effect will take place. The body will give a little bit, will reach equilibrium, and the net effect, say, on an observing spacecraft will be zero. If the body had already cooled and there's a rigid surface, it will not do this. Then it will have to hold the mountain up, and that will cause a gravity anomaly or an additional gravitational effect that will be observed like this. So that's one of the odd cases that are interesting. The other one is, what if you fly over a flat area? You look at the topography, you look at the images, there are no mountains, no valleys. You would expect the orbit to be straight. But you do that and you see a dip closer to the body. This was actually observed at JPL with early lunar missions, and it turns out that there are subsurface material that have higher density that are causing this. These are typically impactors, little meteorites, asteroids that have hit the moon over its geologic history and created a crater, a big hole, and the object stayed in it, got buried. And over geological time, the whole feature got buried. And now you look at images or the topography, you don't see it, but subsurface, it's still there, and it has a gravitational effect. So this could only be discovered by gravitational techniques. And this is called the mass con, by the way, short for mass concentrations. Yes, we're that lazy, even that we have to be abbreviated. I mentioned looking at the topography from images, but this is the topography of the moon from the ongoing LRO, Lunar Reconnaissance Orbiter, that has a laser altimeter and can measure the highs and lows using laser altimetry. And this is a beautiful picture, color-coded, just to show the highs and the lows. But it shows typical craters of all sizes at the moon. So now we can produce a gravity field, and we're yet to talk about how we do that. That's coming. And we get a topography field, again, an expansion over the latitudes and longitudes of the planet, of the body. And the thing to do is to compare them, called correlate. And then the comparison gives you a geophysical model about the interior structure. So just from correlating the gravity and topography, you can deduce or kind of convince yourself you can get a model about the thickness of the crust and its density and the elastic thickness of this layer, the lithosphere, that might be rigid or flexible depending on whether it was warm or cooler when mountains and other loads were placed on it. And additional geophysical information that we can get. Sometimes the solution that you get is not unique. There are various scenarios that can give you the same numbers. So that's when we need independent confirmation from other measurements, other instruments, other observations, the geochemistry, the rock, petrology, or additional geological information. And those typically pin down competing models to one that we would think is correct. And this collection of information will give us the internal structure and something called the thermal evolution. I've already alluded to what thermal evolution means. It is the cooling process. Things started warm in the solar system and cooled, and in the process, things have formed. Differentiation, which is a separation into a crust, a mantle, and a core, and so on. So this comparison between gravity and topography, there's a mathematical function called admittance or correlation. Takes into account the surface loads, meaning these are topographic features on the surface, highs and lows, mountains and valleys. But it turns out there are subsurface undulation as well in the MOHO layer. So these could also have a gravitational signature. So that's why to isolate subsurface stuff, we need to first remove the effect of the surface topography. So what do I really mean by that? We can assume a density for the rocks on the moon. So we say the mountain is this big, it's this density, it must generate a gravity signal of such and such. So we'll remove it from our observation, and so on. And what's left must be due to subsurface features. So from that, we can actually create a map of the thickness of the crust for the whole moon. This is the near side, always facing Earth, because the moon is in gravitational lock with the Earth, such that from the surface of Earth, we can only see one side. We just call it the near side. And this is the far side, which it turns out looks different. And it is the far side, not the dark side. I believe that came from a popular song. And it appeals to people because there's this common thinking that maybe the far side doesn't get light, but it does obviously get sunlight, and it's not a dark side. The moon, it turns out, has one big hole near the South Pole, mostly on the far side, and it's called South Pole Aiken. And that is probably about 10 kilometers deep at its the deepest point. In fact, it excavates the entire crust, so you can see here the color coding 0 to a few kilometers in this area. And we can get in up to 100-kilometer thick crust in the blue area. So it varies in thickness, just like on Earth, between continental and oceanic crust, thickness variation. This is a notional view of the lunar interior. Most of you have probably seen a similar image of the Earth showing a core, inner core, outer core, mantle, and crust. Similarly, we now think there is probably a solid inner core and a layer of a fluid outer core. In fact, one of our objectives is to hopefully determine that, confirm it, or constrain it. And a large rocky mantle and a thin crust that the astronauts have stood on. These are the landing sites of a couple of the Apollo missions, 12, 14, 15, 16. And so this is the near side, and this would be the far side, and this would be the South Pole Aiken I showed earlier. All right, the thermal evolution involves temperatures and heat coming and going, heat sources and heat sinks. And the moon has external and internal heat sources and sinks. But if you can see in this cartoon, and I can't see it very well in this light, but this is an image where a piece of the moon was taken out for you just to reveal a potential presence of a liquid core in the middle. And it is small. It's about maybe 20% the radius of the moon. Or by way of contrast, Mercury, we now think, has a core that's about 70% of the planet, so it's huge. So that probably had a different thermal history. So what adds heat to the moon? It's the impacts. Every time these asteroids and meteorites hit it, they deliver energy, and that makes it into heat. And what makes it cool is just radiation. It's exposure to outer space from the surface, the cooling process. And internally, there's radioactive material on the inside, just like there is on Earth. And as the radioactive material decays, heat is generated, and that causes convection, as in mantle convection, where the rocky layer turns and moves over geological timescale, which is millions of years. So it turns out that the cratering process is a key piece of the story to determining the age and the thermal history. As you all know, there are no craters to speak of on Earth. I mean, there are one or two that are actually preserved, but it doesn't mean Earth never had craters. It just means that Earth, being a living planet, had recovered and filled them in. The moon probably cooled earlier, being a smaller size, and then was what I would call a dead object. So the craters would leave permanent impacts, and they come in all sizes. And there are a group of scientists whose specialty is to determine from the size, diameter, as well as depth of craters, their age. So one can start dating the features just from the type of craters, their sizes, and their diameters. I should also go back and tell you that we can date or determine the age of large features such as mountains and craters, again, from whether they are compensated or not by the lower layer. So if the object was placed, quote unquote, when the moon was still fluid, it would probably sink enough to reach equilibrium. And if the moon was cool, it would probably stay as a load in the gravity signal. So then right away we can, when we correlate with the topography, if it's still there, it's probably of a certain younger age, so it occurred after the cooling process. There'll be time for questions, so we can dwell on that. Okay, so this is another image that kind of dwells on this. Now, it turns out, like I mentioned, that the moon and Earth are actually close in age. So this formation process happened early on where the Earth was still fluid, but has had enough time by itself to differentiate into a core, a mantle, and a crust. So the early lunar lithosphere, this layer below the crust and has a piece of the mantle in it, probably cooled quickly enough to support large loads, large mountains, features from gravity information we have to date. So we've already seen features. This is called Orientale Basin, if you're the type who likes to look at maps of the moon and know what the features are. So we already know that in many cases that the cooling process was quick and the features appear after the correlation takes place. We're interested in detecting, constraining, whatever the right word is, really determine if there's a core, especially a fluid core in the moon or not. So if there is one, a little pie slice of the moon would look like this, with a solid inner core, a fluid outer core, a mantle, and a crust, and Earth looks exactly like this, but to a different scale, bigger scale. So now I'm not going to get into a lot of technical details with terms that we use, the gravitational oblateness, the shape of the equator, but we look at parameters like these from the gravity field that we produce. We call these the low degrees or long wavelength effect, and we watch how they change as a function of time. Now, if you measure the gravity today and you come back and measure it tomorrow on Earth and it changed, you can probably figure out why. And in fact, Mike will talk about why in additional detail. There are things on Earth moving, the atmosphere, water, things, climate, things of that nature. But on a dead object like the moon, it should be the same. So if it changes, it probably means there's a liquid core, just a small fluid layer that causes lubrication, literally, between a solid ball on the inside and another solid layer on the outside to cause independent motion. So if you have a top and you spin it, and if it's made of the same solid material, it spins in a certain way that we can determine. But if it spins in something different, you start becoming curious about what's made on the inside. If you create a model where the top has water, something, and a little ball on the inside, it will spin differently. So we watch the spin behavior. And in fact, this has been done for years now. Since the Apollo era, the astronauts put a little reflector on the moon that can reflect laser beams from Earth. So we've been doing this. We've been sending lunar laser ranging to the moon for decades, and we've collected enough material that we can actually determine the physical vibration, this spinning and the variations, the odd variations in the spinning of the moon. And we combine that with gravity information that we get from spacecraft, which gives us this oblateness, polar and equatorial. And the combination of these, especially the time-varying aspect, would tell us whether there is a liquid layer causing independent motion between two pieces on the inside. Okay, I need to speed up a little bit so that we can cover the rest of the material. I'm going to ask Mike to come up and talk about the technique that we use. So far, I've told you the science objectives. If somebody gave us a gravity field of the moon, I can go back and tell you the correlation between it and the topography. I can tell you if it has, hopefully, if it has a core on the inside, its thermal history, has it been solid or fluid when topographic loads were added. But the trick is getting this gravity field. Now, this has been done before at the moon as well with spacecraft, but all of them use this traditional style of a single spacecraft sending a radio signal to Earth. So there's a line of sight for the radio signal from the spacecraft to Earth. Now, because the moon does not show us the far side, we only have gravity from half the moon and practically zero knowledge of the gravity from the far side. So we need to invent another technique that will overcome this obstacle. And it turns out there is one already being utilized on Earth. So let me bring to the audience Dr. Mike Watkins. He's the project scientist for both GRAIL and GRACE, which is the equivalent for the Earth Gravity and Climate Mission. And then we'll come back and show you a little video and take some questions. Mike?
All right, thanks, Sammy. So Sammy and other lunar scientists, including Maria Zuber, who's our university PI up at MIT, they have kept asking us for a long time here at JPL, those of us that build satellites and design satellite missions to measure the gravity field, think of something to measure the far side of the moon gravity field. In fact, that's where a lot of interesting stuff is. The far side's different from the near side geophysically. There's this South Pole feature, this Aitken Basin that Sammy talked about. And all of our traditional methods for mapping the gravity field, which is tracking a satellite orbiting the planet using the big antennas out in the desert there out at Goldstone and around the world, the Deep Space Network, all fail because the moon gets in the way, right? So we're watching the moon on the far side, on the near side, and then it just gets eclipsed by the moon, then we don't track it anymore, and it comes out the other side. So the way that we realized to handle that was simply to put another tracking station in space, basically another satellite, and track our one satellite, our little test particle, our Newton's apple, with another tracking station that we also built. And that is hard because it involves building two different satellites and keeping them pointed at each other and tracking them very precisely and knowing the orbit of the one that you're tracking with and all that. But we actually did that around the Earth in 2002 with a mission called GRACE. And as soon as we got that working, we realized this is really the way to catch the far side of the moon as well. So the way this works is we have one satellite tracking another satellite, and they're a certain distance apart. And so as Sammy showed, one satellite in orbit kind of being attracted by a mountain or less attracted by a trench. What we actually do here is we look at the separation. We measure the separation between the two spacecraft by tracking each other. Let me turn this on. Here we go. Okay, so we know that the two spacecraft, here are two spacecraft, GRAIL 1 and GRAIL 2, are a certain distance apart. And you might think of this as being 100 kilometers or so. And we're measuring it with microwave ranging between the two spacecraft. Happens to be K-band, so a few centimeter wavelength. So you're tracking between these two guys here, and we measure this distance of 100 kilometers or so very, very precisely. In fact, we measure it to just a few microns in distance. And as this guy comes up on this mountain here, they get pulled a little bit farther apart, all right? Because we're at some distance apart, and then this first guy starts to feel the gravitational attraction of this mountain, and it gets a little farther away from its partner. Step 2. Step 3, as we're leaving, they're each kind of getting attracted by this mountain, and then finally the trailing guy is still feeling the effect of this mountain, right? So they get pulled apart from their nominal position, get pulled apart, kind of come close together again, get pulled apart again, and then go on to the next spot. And they keep doing this little dance. They get closer and farther away and closer and farther away and closer and farther away, and we map all that out around the orbit. And we correlate each one of those little expansions or contractions of that distance that we're measuring to a few microns with the subsatellite point. So that's all fine and dandy, and it works perfectly, right? Well, there's a few things that also cause the orbit to change. And this is where the nasty and ugly engineering gets into this beautiful science problem. So one of the big problems we have is that, so think about around the Earth, there's a little bit of atmospheric drag even up at satellite altitude, and one of the satellites hits a little clump of air and gets slowed down, and or the trailing one hits one, and they separate a little bit because of that, and you need to say, oh, that wasn't gravity, forget that. Okay, well, the same thing happens, even the moon has no air, it's got some other things going on, right? It's got actual direct radiation pressure from the sun, right? The actual energy from the sun blows on these spacecraft a little bit, think of them like a kite, and pushes them away in their orbit a little bit, so we have to measure that. And in fact, we know how big these are, we know how reflective they are, we know how much energy the sun is putting out, and we actually model this away as best we can. And because it's kind of small compared to gravity, we don't have to model it perfectly, but we do a pretty good job knowing exactly how the satellites are shaped, how they're pointed relative to the sun, and in addition, how much they're heating. So this solar radiation pressure also heats up the spacecraft, and in addition, we have electronics boxes like your TV at home generating a lot of heat, and they radiate heat out. The back of the spacecraft, from the satellite bus, from the solar panels, that heat causes a little bit of thrusting on the spacecraft. So they'd move in their orbits because of that. So we very carefully balance where the thermal radiators are. We try not to turn any instruments on and off. Once we get to the moon, we leave everything on all the time. We try not to even switch camera heads, not to do anything, to keep all of this as constant and modelable as possible and not look like, oh, I'm flying over a mountain. And that caused a little change in the orbit. There are some paints and glues and water and all kinds of crazy stuff on the spacecraft that we can't completely bake out, right? We're here in 1G and with atmospheric pressure. We get it out in space and suddenly stuff kind of starts to boil off, right? Little stuff that was chemicals that are inside the spacecraft, including water, start to boil off. That little boiling off causes a little bit of thrust on the spacecraft, and we're trying to be careful about that as well. In fact, that's part of the reason we take a little bit of extra long time to get to the moon. It gives more time for that to stop. So there's a lot of details that could look like gravity that the engineering team here at JPL and our colleagues at Lockheed Martin who built the spacecraft spent a lot of time trying to make sure that we have all these under control and that they don't look at all like the gravity field so that we can get the cleanest possible measurement of these small orbital changes that are just due to the gravity. Okay, just like the spacecraft gets heated up by the sun and gets shined on by the sun, the moon gets shined on by the sun, and then the moon radiates back to us. It radiates both in the visible spectrum, that's why we can see the moon at night, and it actually generates heat as well. So it's even the part that's when the sun is not shining on it, right? And the sun is partially set on some part, it's still radiating, right? You can still feel a boulder in the desert after the sun is set. So a lot of heat is coming off the moon, and we do the same kind of calculations we do for energy coming off the moon that we do for energy coming off the sun, and we have to handle that as well. And these perturbations are actually pretty big as well. These can be about as big as the effects coming from the sun in some cases. Now, all of that would be difficult from both the engineering and science analysis system if we hadn't done it before. So we did it before on this mission called GRACE. So GRACE was 2 spacecraft launched in 2002 to measure the Earth's gravity field. And it's the same story here. 2 spacecraft, these are solar panels around them, and this is a picture of the K and K band ranging between the 2 spacecraft. Now these guys observed the Earth's gravity field exactly like Sammy was talking about for the moon. And they do it very, very accurately. Here's a picture of how well we knew the gravity field, for example, in a kind of defocused way before we launched GRACE. This is sort of using every satellite we had ever tracked one at a time to measure the gravity field. So we take all their little orbits and how much they adjusted and make a gravity field of what the subsurface gravity is as Sammy was talking about. And here's just the first 100 days of GRACE. So GRACE did this accurately enough to get this into focus, and here's the first year of GRACE. So we're able to pull the gravity field into very good spatial focus with this technique. However, that wasn't the purpose we did GRACE. And the reason is we live on the Earth, and so even though we learned quite a bit more over the oceans and stuff about the gravity field, we know quite a bit about mountain range gravity and stuff on the Earth because we live here and you can go measure it. You can take a gravity measuring device, a gravimeter, and set it right there on a mountain. You can set it in your backyard and learn about the gravity field, which you can't do on the moon, of course, or on Mars. So getting this mean gravity field was useful and useful in some areas where you can't go put something down, like the middle of Antarctica and the ocean. But what we really wanted to do was get rid of this so we could see changes. And something is changing on the Earth, as Sammy noted, that's not changing on most other planets, and that's water moving around. So although it didn't seem possible from a little thing of water like this, if you've ever carried a 1 gallon or a 5 gallon thing of water, you know how heavy water can get when it gets to large quantities. So when it rains a lot in the tropics, in the Amazon, it's raining millions and millions of gallons. The weight of that water actually affects the satellites in their orbit. And we made GRACE accurate enough, actually about 10 times more accurate than GRAIL, so that we could observe that. And over the 8 or almost 9 years that GRACE has been up in orbit, this is how the gravity field has changed. This is sort of, forget about the winter and summer, just look at the sort of the end of the mission minus the beginning of the mission in equivalent centimeters of water at the surface, and what you see is glaciers in Greenland having melted. So Greenland got lighter. So there's less gravity there, and the satellites could see that there was less gravity because we've melted a lot of ice off Greenland, and folks have seen a lot of press coverage about that. We've melted a lot of ice off West Antarctica, Antarctic Peninsula, Patagonian glaciers, for example, and Alaskan glaciers. So you can see this very clearly. You can also see some drought features due to water extraction. Here's a persistent drought in the southeast US, same in the outback of Australia, and the same in India here. There is one feature that is kind of climate related, but not on human timescales, and that's this feature that's a positive growth in gravity here over northern Canada, centered on Hudson Bay. That's actually the viscous response. Remember, Sammy's talking about the fact that the Earth is still living and viscously responding to the last ice age. So at the last glacial maximum, there was tons and tons of ice in this area, and it depressed the Earth enough that when it melted off, the Earth is still rebounding and coming back here. So the Earth is pouring mass from the mantle back into this area. So this is actually viscous rebound. And scientists use that both to learn about the last glacial max ice loading, as well as how viscous the Earth is. What's the Earth made of in the mantle that would cause it to respond at the rates that we're currently seeing. So GRACE has been a big success, and we have a GRACE follow-on mission coming to launch in 2016, and GRAIL's in between those two missions. So when we got GRACE working, met with our lunar colleagues again, and proposed the GRAIL mission. So the GRAIL mission is exactly as we talked about, 2 spacecraft launched on a single Delta launch vehicle this September. The mission itself is reasonably short. We take a few months to get to the moon and just a few months at the moon. 82 days of lunar gravity. We just have to cover the moon really a couple of times, once or twice, to make sure we covered everything. And then since it's not changing much, we don't have to keep doing it, unlike the Earth where you want to keep watching it every month or so. We've got some cameras. Sally Ride, who many of you may know from their time as an astronaut, is our EPO lead with some cameras used that students can target. And we measure the distance between the spacecraft and actually the velocity, the change in distance using the Doppler at Ka-band microwave. And of course, we still track it from the Earth and get telemetry down as needed. We're in partner with our scientist friends at MIT. Lockheed Martin Denver is building the spacecraft. Goddard's going to help do gravity fields along with us, and Sally Ride is doing the EPO. So we have a brief video here that's useful to show. So let's see.
Go to view, full screen.
GRAIL is a mission which is going to study the interior.
So this is Maria from MIT
of the
talking.
moon. We'll be launching towards the moon using a Delta 7920 heavy launch vehicle from Launch Complex 17 in Cape Canaveral, Florida. This rocket is going to place the 2 GRAIL spacecraft into a parking orbit around the Earth. From this parking orbit, we'll do an insertion burn, which will send the 2 spacecraft towards the moon. After this insertion burn, the 2 spacecraft will be released from the launch vehicle fairing, one at a time, about 8 minutes apart. They'll then come into view of tracking station, and we'll deploy the solar panels so that the 2 spacecraft can power each other.
So we keep the spacecraft
The
very
2
small
spacecraft
so they can
will
be on the
then
same
go
launch
towards
vehicle.
the moon.
Saves us money and
Unlike
makes
the
our life
Apollo
easier.
missions Where we sent astronauts to the moon in 3 days, these 2 spacecraft will take 3 months to get to the moon. We use this low energy trajectory so that we can pick what day we want to get into lunar orbit, no matter what day we launch. This heliocentric view shows the trajectory of the GRAIL spacecraft from the Earth to the moon in blue relative to the position of the sun, which shows the different mission phases. The 2 spacecraft will insert into lunar orbit independently of each other, and they will both go into separate large elliptical orbits around the moon, and over a period of a couple of months we'll do a series of up to 12 burns to take energy out of the orbits and lower them into the GRAIL mapping orbit. As we get towards the mapping orbit, the two spacecraft will line up so that they can begin to range to each other. The mapping orbit is about 50 kilometers above the lunar surface. It's a polar orbit and will vary the distance between the two spacecraft so that we can sample different depths within the lunar interior. These two space...
Okay, so I think that's enough there. I do want to highlight one aspect here, and that's this period here. All of these represent maneuvers by the spacecraft to make sure they get into the same orbit, into this mapping orbit. One spacecraft at a time, right? They're launched on the same launch vehicle, but then separate and fly to the moon separately and have to get back into this formation. And so there's a lot of work by the ops team. So the mission design, the navigation folks have to do a lot of work to make sure each one of these burns comes off just right and gets the two spacecraft from their translunar orbit into the right mapping orbit. So there's lots of fun there for a few days by the ops team. Now, since this video was made, a lot of work has happened. Yeah. Let me catch back up to where we were here. So since the video was made, a huge amount of work has been done by the spacecraft team here at JPL and up in Denver to put the spacecraft together. So the spacecraft would look like this. They've got a couple of components on them. They've got our famous K-band ranging system here between the two. We've got to send time between the two spacecraft so we know what time it was transmitted and what time it was received. If we had GPS, which is what Grace used, we wouldn't have to do this, but there's no GPS at the moon, so we have to send our own little timing signal as well between the two spacecraft. We have to transmit information back to the Earth so that we can do both tracking and get telemetry and correlate the time on the spacecraft with DSN time as well. And all of that stuff has been built. So this is the bus structure. We've got the avionics system. We've got the gravity processing assembly. This is the radio science beacon that sends X-band signal back to Earth. This is the ultra-stable oscillator so that the frequencies stay perfectly constant when they're transmitting to us. This is the K-band ranging assembly, the flight computer, the fuel tanks, solar arrays, star cameras, everything we need, reaction wheel assembly, and on and on and on. And here they are. Here's the solar array integration, and here is an assembled GRAIL spacecraft. And you see it's not real big compared to some spacecraft. It only has to do one thing. It only has to transmit the K-band signal to the other spacecraft and get that information back to the Earth. And we want to fit both these guys together inside the fairing on the Delta and light enough that the Delta can get them to the moon. So these are fairly lightweight and fairly small spacecraft by interplanetary standards, but the very focused nature of the GRAIL science investigation is what allows us to do that. We don't have to carry a lot of other instruments to do high precision altimetry or photography, things like that. So currently, we are still on track to launch this September, and as Maria sometimes says, we get to play with the moon as adults, and that's a good thing. So, thanks for your attention.
We have a microphone. If you'd like to bring your questions forward, be ready for that.
Yeah, we'd be happy to take questions.
Okay. You showed that, well, of course, the moon being tidally locked to the Earth, and there's a little play back and forth, a little libration. Does it still make sense to say that the moon is locked with one side because the crust is thicker on one side, or is that partly what we're trying to find out here? What does that whole thing tell you about the structure in and of itself?
The gravitational lock itself has not affected the difference in the crustal thickness. But as it happens, the far side is mostly thinner, but it's due to this large impact called South Pole Aiken. So you can think of it as it's showing one side to Earth, and Earth is protecting it from outside impacts, but the one exposed to space has received more hits that have thinned out the crust.
I have a question about helium-3. If helium-3 is emitted by the sun and it goes to the moon, and the moon having no atmosphere. It's in plenitude, whereby the Earth has an atmosphere, and so it's very scarce on the Earth. If it is plentiful on the moon, how can we separate it from the moon's soil? How can we heat it? How can we transport it? And how can we create nuclear fission into nuclear fusion using helium and one proton?
Okay, a question very relevant to GRAIL. I'm just kidding. It's a different subject. But what happens at helium and all emissions from the sun, as you said, because the atmosphere, the moon doesn't have an atmosphere to protect it, they actually get buried in the regolith of the moon. And from chemical tests to date on samples, as well as orbiting spacecraft, we've detected these gases. Now, what you're talking about requires a manned, quote, manned space program that can install factories and processing facilities and the like. And that's it's a bigger question, has to do with funding and national priorities for such a program that is, like I said, outside the scope of this mission.
It would be dependent on cost then.
Yes, it's very costly to do such a thing.
Thank you.
Thank you.
Hi, I was wondering, in the early moon, was there something similar to Earth's plate tectonics that would create the mountains and valleys that were shown earlier?
People have speculated about this, but so far there are no evidence for plate tectonics as we have defined them for Earth. There is activity such as volcanism, but magma eruptions from the inside, but that's because the entire body was very fluid at the time. So the current thinking is that it's not quite plate tectonics as we know it, not even for Mars. That's still, I think the jury's still out on that as well. Good question.
I have two unrelated questions. The first is you had a slide that showed how the history of the moon is governed by its heat history, and that one factor in the heating is the radioactivity. Is the radioactivity per unit of mass in the moon about the same as the Earth, and is the moon cooled down because it's just so much smaller, or was there a difference in the amount of radioactivity?
There is a difference in the amount of radioactivity because it's proportional to the amount of material and type of material and the rocks. But it also happens that the smaller body would cool faster. So there's still radioactive material on Earth to this day. So there's something heating and something cooling, but the net effect is that every planet is cooling, the entire solar system.
So it's the size mainly that's governed the difference.
Correct. And the fact that I was going to say the fact that there's no iron in the core, or we don't think there's an iron in the core.
The other question regards the ranging system. So you say the K-band is a couple of centimeters in wavelength, and yet you're able to measure the distance down to the micron level. Is it? But you mentioned you're using Doppler. Is somehow the Doppler allowing you to get so much slower than one wavelength?
Well, we actually can measure the phase of that centimeter wavelength thing to better than 1 part in 1,000, and we do that several times per second. So when we average for a chunk of the lunar surface, we get the equivalent of a few microns, and then sometimes it's easier because you remove some biases to look at the velocity rather than the range, so the difference in successive ranges. And that gives you numbers in the micron per second range. But it's really our ability to do part per 1,000 or so phase resolution on those wavelengths, and then to average that over a few seconds that really gives us that extra precision.
Thank you.
These are questions from Ustream. How does varying the distance between the two satellites increase or decrease the study depth?
What was the last phrase?
How does varying the distance between the two satellites increase or decrease the study depth?
Yeah, so that was a comment in the video. So it's not real sensitive, by the way, but technically, if you remember the video, when the first one's kind of getting pulled toward a mountain, and at some point they're both kind of pulled this way, and then the last one's kind of still feeling that pull. The amount and the frequency of that separation varies with the distance and with the separation distance. And the best way to think of it is if I'm looking for a very large wavelength feature that affects both of the satellites almost the same, most of the time the spacecraft are flying together over that distance. And so the further the separation is, the more I can see these very long wavelength features that tend to be deeper in the crust. When I'm looking at a very short wavelength feature, then that is amplified by the spacecraft being closer together because I can get the spacecraft on either side of that feature. So if you kind of believe that longer wavelength features are deeper in the crust, a little longer separation improves your sensitivity. And if you believe shorter wavelength things are up near the crust, then closer together is better.
I have 5 more questions from Ustream. Will the magnetic maps of the moon be of any use with the GRAIL data to further understand the lunar core?
Again, I didn't catch the first part.
Will the magnetic maps of the
Magnetic
moon...
maps. Okay. Yes, the short answer is yes. That's because we've discovered that some of the rock samples actually have a remnant magnetic field on the moon. But we know now there is no dynamo. There is no magnetic field as Earth does. So chances are that there was a dynamo magnetic field that had died, that stopped working, and then what was in the rocks got froze that way. This happened on Mars as well.
My next question is, I'll take one more and I'll give you a turn, since you have a GRAIL shirt on. How did the astronauts deal with the heat and gravitational pull when they went there?
Very carefully with very protective suits for the heat. So in fact, one of the, I don't want to call it side effects, but one of the benefits beyond the scientific interpretation we talked about of having a very accurate gravitational field is that it will help future manned mission astronauts land safer. If you imagine when I talked about the mass cons, the buried mass concentration that is not visible in pictures or topography, imagine the incoming vehicle has people in it and they had miscalculated the amount of gravity pulling them down, it could lead to an accident. So there's a benefit from having a very accurate gravitational field for the manned program as well. Somebody with a GRAIL logo on their shirt.
Yes, I was part of the team that developed and tested the GPA instrument, and I've been curious for a long time. I was wondering if you could elaborate on how the S-band timing measurements and the Ka phase measurements are actually processed into a gravity field.
Okay. So the primary link is Ka band. It's about 32 gigahertz, the definition of that band. So that is the link each spacecraft transmits and receives from the other one. So the variations in that separation ultimately leads us to recovery. That's why I call gravity recovery, ultimately recovering the gravity field. But it turns out there are 3 clocks that we have to worry about. The payload itself, the instrument that you built, has a clock, the ultra-stable oscillator. The spacecraft system has a clock, and the deep space network where we ultimately receive the data has a clock. We need to coordinate knowing the time at all 3 very accurately, and I mean down to relativistic effects, in order to be able to tell the little feature, little blips of gravity, where the location was from orbit determination. So the timing from the S-band is key to ultimately telling us the location of the feature that we're seeing in the K-band gravity data. That's the short answer. Does that help?
So if your question was specifically if you're instrument savvy, so the thing is the signals are one way. Okay, so this guy transmits to this guy, and this guy transmits to this guy. It doesn't round trip, like it's not bouncing off and coming back. And so when this guy sends a signal to this guy, he says, I'm sending you a signal at time X. And this guy says, I'm receiving a signal at time Y. Now, if those are free running, you can't know what the time of flight was. So this guy has to say, well, time X occurred at this time that you transmitted it. So we need some way to sync up what time this guy thinks it is when he transmitted it to what time this guy receives it. And that's what we have to actively transmit. Now, GPS on the Earth allows you to do that because they're each connected to GPS clocks. So to enforce that to allow synchronization, simultaneity to be identified. But here we have to do that transmission between the two so that it can know when the one-way transmit and received should have happened to compute the time of flight.
I guess my question is more geared towards how do you take the raw S-band phase data or maybe find information about this?
We'll show you. We have an algorithm. Yeah, we have an algorithm description document. I can show you exactly how those phase combinations are made, and we can talk to you offline.
Next question. If GRACE was sensitive enough to measure the gravitational influence of rain in the Amazon, was it sensitive enough to measure the increase in mass of the island of Hawaii due to Kilauea?
It's very, very hard to see volcanic activity because it's usually very confined spatially, and it doesn't move mass a long distance. The spatial scale of these tropical monsoon activities is really incredible, and it's also moving water from a long way away. It's not moving it just from neighboring from 50 kilometers away to somewhere else or just vertically in the earth. So it's almost never can see volcanic activity. It's tough. We can see big earthquakes, but the amount of mass transported by these monsoon activities is kind of mind-blowing.
One more, I'll give you a turn. Would a future GRAIL-type mission benefit from some sort of moon-based telemetry device, maybe for accuracy?
Yes and no. There are a lot of advantages from moon-based tracking systems. The hard part is a lot of them having to do with understanding what the moon is doing, like these retroreflectors did. Sometimes they help track the satellite. The problem is you might ask yourself, why did we do GRACE this way since there's no far side of the Earth, right? And the answer is it's hard to put one tracking station on the Earth and observe the whole satellite all around the Earth. We have to put 100 tracking stations all over the Earth to observe GRACE everywhere it went. So the same is true on the moon. You know, if we had a GPS at the moon, that would really help us. And at Mars, I work on Mars a lot, so GPS on Mars would be a big help too.
Yeah, this question has to do with the surface history. We know that on the moon we have different regions, you know, volcanic regions like the Maria, and then the highlands and the fractured rock and all that sort of stuff. And there have been places on the moon where we know there's been volcanic activity. The Maria are obviously volcanic in origin, but there aren't a lot of places where you can definitely say there's a volcano. Oh yeah, that's a volcano for sure. Once we have this entire moon surface and interior mapped gravitationally, we'll be able to help identify with the gravity maps these features as being, yeah, they're volcanoes because they're denser or lighter or what have you?
I personally don't think so, because the volcanic activity, although it lasted millions of years, that was a few billion years ago. So if you're actually looking for the classic volcanic-shaped mountain with the blown-off top, we're not going to see that. So in fact, we already have sufficient topography, sufficient resolution to look for things like this. So what happens is that the magma erupting from volcanoes created a magma ocean that's pretty big. And then it dried, and now we see material that, as you have described, dark in color or light in color, depending on if it's a lowland or highland. But to actually capture specific locations and say, that's probably a volcano, if we don't know that already, I doubt that high-resolution gravity would do that. But I might be proven wrong. We'll see. There's always a discovery element in new data and the excitement of the research.
Thank you.
Before I ask the last question, just want to remind everyone that this talk will be given tomorrow at PCC at 7 p.m. And here's the last question. Why was the flag waving when we first landed on the moon?
Well, I will just say that this mission here is not a simulation. This mission is actually going to go to the moon. That's my answer to that, as did the Apollo astronauts. But I guarantee you this one is going.
I'm curious about how you guys organize these efforts. One group is in Colorado, another group is in Florida, and is there an easy way to describe how you begin to map out everybody's position in the effort?
Yeah, it turns out it's not that hard because people who are experts in the field have probably known about each other for a long period of time, and we've teamed up in the proposal phase. We've agreed to work together. JPL has unique expertise, so we keep those areas at JPL, just do what we do best, including navigation, orbit determination, gravity solutions, the mechanics of processing the data. But the interpretation part, once you have a gravity field and a topography field, that is then given to academics at various universities who are members of our team who've done theoretical work and modeling and things of that nature. So to me, it just seems so natural that there's a smooth collaboration, but I can see how it might look a little mysterious on the outside.
And a lot of frequent flyer miles.
Yes.
You fly business class?
No.
Unfortunately, no.
Sammy, how about, would GRAIL help us understand better the distribution of ice in the moon? Because I think Mike spoke about tracking the movement of water, but how about ice?
Yeah, the amount of ice, and for those who don't know or haven't heard about this, at the poles, the north and the south poles of the moon, some of them are permanently shadowed. They never get sunlight just because they're deep craters and the sunlight obviously doesn't bend to get into them. So over the geologic history, comets might have delivered water to the moon and it would have evaporated everywhere else except these permanently shadowed craters where there would now be ice. And there's been speculation about this for a couple of decades actually. And there's been one mission that actually intentionally crashed into the craters to get the ice to explode and take images, and there's been some evidence of that. But to make a long story short, there's possibly ice on permanently shadowed craters, but we think that the amount is very small, and it's probably not within the, and it's probably not moving much to show gravity variation. So I doubt that we can actually contribute to that problem, which is very interesting, especially for the human program to have water not have to transport it from Earth.
Yeah, the lack of movement is really the thing that prevents us from seeing it, right? That the ice being just there permanently is really not visible with GRAIL. If it moved around a lot, from polar caps or something, we could see that. And in fact, on the planet Mars, where the polar caps do change seasonally, we actually can track polar cap movements pretty effectively. So if there were polar caps on the moon that transported that ice, we would be able to see them, but I think it looks like it's a much more static situation on the moon.
I want to add here some trivia for you. It turns out the closest planet to the sun, Mercury, should be the hottest, receiving the most amount of heat, has frozen polar caps. So go figure. So the processes are different at the poles.
I don't have a question, but in case some of you have to leave, I want to thank the speakers, and my pleasure to introduce you tonight. It's a terrific mission. Thank you for doing this tonight.
We've enjoyed this. Thank you. We'll be around if you want to come up and ask questions. Thank you.